So before we get into solving tougher differential equations, we need to review some properties of exponents, which will help us when we go through this whole process, okay? Some easy ones. You know, if I have two of the same bases taken to different powers, then you just add these powers together. This is x to the fifth, but I'm going to write it as x to the 2 plus 3. Because what we will find is that when we have x or something to a sum of two or more powers, we will want to rewrite it sometimes as a product of our bases to the two separate powers. Okay, it's very important that this is a multiplication sign in between x to the y and x to the fifth. X to the y plus 5 is not x to the y plus x to the fifth. This can't be simplified, and that's not that. Okay? Why is that going to be helpful? Well, we're going to see some situations where we have e to the power of some variable plus c. And I can use this property here to rewrite this as e to the x times e to the c. And sure, that's great. But we can go a little bit further. If we say c is just a constant, well, e to the power of c is just a constant as well. I can rewrite e to the c as c. And I can actually move that c to be in front of the e to the x. So all of a sudden, e to the x plus c can be written as c e to the x. And we will be using that frequently today. Some others, if I have x to a product of two things, this is 2y, it doesn't have to be written as 2 times y. We can write this as a power to a power. This is x squared to the y power. When we have a power to a power, we multiply our powers. That helps us simplify something like this, e to the 1/2 log x. I can rewrite this as e to the log x to the 1/2. And why do I do that? Because we know that e to the power of log x is just x, and this is x to the 1/2. Okay, that also kind of creates a log property that we can use. If I just looked at 1/2 log x, or something like k times the log of a property of logarithm says you can rewrite this as log of a to the k. Why does this property exist? Because logs deal with exponents. It helps undo e to powers. So they're kind of already in kind of a form of where they're in a power. So we know x to the 3y can be written as x cubed to the y. It's the same thing here. This was just k log a right here, be log of a to the k. Okay, some other things. Solving e to a power for that power. So solving for x when you have x in the power of e. Solving for x when you have x in a log. How do we solve for x? Well, if it's in the power of e, to undo what log is doing to e, we would take the natural log of both sides. A lot of people like to think that this is multiplying both sides by log, and that's not it. You could think of it like it, but it's not. You're taking the natural log of both sides. It's like a function. And when you take the natural log of e to the x, you just get x. And on the right side, you'd write the natural log of 5. And here, if we want to solve for x and get x outside of the natural log, we would take e to the power of both sides. I like to write the e right underneath. I like to use a caret just so that you can see that I'm taking e to the power. This is not multiplying both sides by e. It's taking e to the power of both sides. Because e to the log x will undo each other, just leave us with x is equal to e to the 4th. Okay, it's just algebra. It's equations doing the same thing on both sides of the equation. All right, we will have to take situations like this and solve for y, where we have a plus c, we have some stuff, and we need to solve for it. Well, y is inside of the natural log. You should immediately be thinking, take e to the power of both sides. Now the right side has some addition, so when we take e to the power, make sure you understand that the entire right side needs to end up in the power of e, even though there's a plus c. So this would be y equals e to the 5x plus c. Well, that's good, that's sufficient, but we can actually rewrite this using those exponent properties as e to the 5x times e to the c, and we can write this as c e to the 5x. Because c is just a constant, e to a constant is just another constant. E is a number, to the c is a number. We can talk about how, well, c could be a positive or negative, but all of a sudden e to the c is just going to be a positive. But once we turn it into a c, we can see that ends up, it works out based on the original problem and the domain of the original problem that we can write it as just a c. Right? Same thing we were talking about earlier with Mr. Brissett. 2 times c, we could just write a c. Now we can say e to the c, just a c. Okay? If I have y in the power of e and I want to solve for it, we would take the natural log of both sides. It's just very important that if you have a plus c, you would not be taking the natural log of c and saying it's a c. You'd actually have to keep the entire right side in the natural log, and you would not simplify it at all. This would just be y equals log of 4x squared plus c. Leave it. Can't be simplified. Okay? And that's it. We know those properties. We know how to solve for y's and e's and with logs. We're ready to tackle these tougher differential equations. Okay? So here's the first example. We have dy dx equals y over x squared, and we're given an initial condition y of -1 is equal to 3. The process is still the same. We are still using separation of variables. You just find that the whole solving for y process is just a little bit more involved. So let's separate our variables carefully using algebra. You can't just move the dx's, move the y's. We'd have to move the y by multiplying by 1 over y. And I'd move the dx's by multiplying by dx. The x squared would stay in the denominator on the right side. The y would be in the denominator on the left side. And I'd have something like this. Okay, now we're ready to take the antiderivative of both sides and go from there. Same process, separation of variables, then antiderive. Now we should remember that if we have y to the first power or a variable to the first power, we're taking the antiderivative. The antiderivative is log absolute of whatever we have. But we should also know that if the power is not 1, you cannot say that this antiderivative is the log of x squared. This is incorrect. Instead, we need to understand that the power rule can be used, so let's use it. I rewrite that as x to the -2nd. and the antiderivative is x to the negative first times negative 1, or negative 1 over x. Plus a c. Don't forget your plus c. Okay, now they want our answer in terms of y equals a function. So let's go ahead and solve for y. This is a general solution. We do have a solution. We can graph this and look at the solution whose derivatives are y over x squared. But the question asks us for y equals, so let's go ahead and solve. We have absolute y inside the log. We don't have anything in front of the log. Because of that, I can go ahead and take e to the power of both sides. Now, the left side would leave us with the absolute y, and the right side would be e to the negative 1 over x plus c, in the power of e. Well, I can go ahead and simplify this to be e to the negative 1 over x times e to the c, not plus e to the c, times e to the c. And then I can finish this off as writing it as c times e to the negative 1 over x. Now, the right side is always going to be positive. So it works out that the left side is positive because of the absolute value. Why is the right side positive? Because e to any power is always a positive number. Okay? However, let's say the y's could have been positive or negative to start, because you can take any value and take the absolute value and plug it into log. So what we do to get rid of the absolute value is we assign the c a plus or minus. Just like we do with our square roots of x squareds or even powers. Okay? So we have y solved for. Now we will use the point y of negative 1 is equal to 3. Now what we will find is that when we try to find c here, we can almost disregard this plus or minus, and finding the correct c will give us the correct half, the positive half or the negative half. So when I find c, I can disregard the plus or minus. I'll have 3 is equal to c e to the first, negative 1 over negative 1. I'll get c is equal to 3 over e. This is a positive value. We'll end up with just the positive half. Again, it kind of works itself out that you get the positive or the correct c value and the correct half while you're finding c. So plugging c into my y equals gives me my particular solution. Now we should be comfortable with this, but we could rewrite this and come up with a different looking answer, but the same exact answer. In your free response, you might see an answer like this rather than an answer like this. It doesn't mean your answer is wrong. They just did it a little bit differently. Also, in your free response answers, you will see that they will find C earlier. They may find C in this step. That's fine. You could do that if you choose to do that. If I plugged in 3 and negative 1, absolute of 3 is equal to e to the 1 plus c, I'd have to solve pretty much using the same process for c. Or just would have simplified maybe a little bit differently. Okay? You do not have to do it on this earlier step. I prefer to wait until the last step to find c. It's up to you what you want to do. You can find it on an earlier step or a later step. Okay? So that was good practice. Your turn. Go ahead and tackle this guy. dy dx equals x squared y. X is 0 and y is 5. What's y? Check your answer with the neighbor. Go ahead and find that c. So this is the point 0, 5. This is your initial condition. Okay, so plug in 0, 5 to find c. You should get y equals 5e to the negative 1/3 x cubed, I believe. Or positive 1/3 x cubed. Beautiful. Okay, pretty standard one here. Separating my variables, I have 1 over y dy equals x squared dx. Anti-derive, log absolute y equals 1/3 x cubed plus c. But we need to solve for y. E to the power of both sides leaves us with absolute y is equal to e to the 1/3 x cubed plus c, all in the power of e. We then rewrite this as absolute y equals e to the 1/3 x cubed times e to the c. And we can go one step further to say e to the c is just a c, e to the 1/3 x cubed. And we can get rid of that absolute by making this a plus or minus c, e to the 1/3 x cubed. Y of 0 is equal to 5. I can disregard the plus or minus. I will find the correct positive or negative c. I plug in 0. I get c is equal to 5. Poof, we're good. Okay? Sweet. Let's try this one. Hold on. Now, a lot of people struggle on this one because they don't know where to start. How can I separate my variables? Well, use those properties of exponents that we had just been talking about. If you have a sum of multiple things in a power, you can rewrite this as the base to the power, first power, times the base to the second power. So I would start by rewriting the right side as e to the x times e to the y. Right? Properties of exponents that we know. Now, I separate my variables using algebra. Multiply both sides by 1 over e to the y. Multiply both sides by dx. Now, don't go too far forward because many of you will make a mistake if you jump ahead. As I see a lot of students get the antiderivative of the right side correctly. They tell me the antiderivative is e to the x plus c. But when they antiderive the left side, they tell me this antiderivative is log absolute e to the y. And that's wrong. Find the correct antiderivative to 1 over e to the y. Discuss with your neighbors, help a neighbor, and see if we can figure it out. So, key is I rewrite it as e to the negative y. Now, if I have the antiderivative of e to the 2x or something like that, the antiderivative of this would be 1/2 e to the 2x, right? The derivative of e to the 2x would be e to the 2x times 2, okay? We would not be asked to take the antiderivative of e to the x squared. You would not know how to do that. So we don't have to worry about it, thankfully. So really, we use this concept, it's a u substitution concept, to know that the antiderivative of e to the negative y is just negative e to the negative y. That's it. Okay, now we have to solve for y. Everybody in this situation wants to take the natural log of both sides, because it's like, oh, y is up there in the power of e. But make sure you just have e to the power on that left side. Instead of taking the natural log first, I would multiply everything by -1. It would actually stay plus c, even though I'm taking the opposite of everything. It's still plus c. Then, after that, I would take the natural log of both sides, giving me -y is equal to log of, don't simplify because it's negative e to the x plus c. Don't simplify because you're adding. If it was just log of negative e to the x, you could do some stuff with that. I don't even think you could do some stuff with that. I'd have to think about that. But you don't have to. Because of the plus c, it needs to go inside the log. And now we can solve for y by taking the opposite of both sides. Again, it would just be the opposite of the natural log of the entire right side. This is where the whole natural log of is so important. It's not log times. It's the log of the entire right side. Our initial condition was y of 0 is equal to negative log 4. So I'd get negative log 4 is equal to negative log negative e to the 0 plus c. If you want to go step by step and solve this, you could, or you can kind of just figure out, oh, we have negative logs on both sides, so c is 5. Okay? If you don't see that c is 5 right away, you take the opposite of both sides, take e to the power of both sides, take 4 equals negative 1 plus c. c is 5. But not necessary. Giving me my solution, y equals negative log negative e to the x plus 5. Okay? All right, go into your free response packet and do number 1.
Why did you go from negative y or you give an
So before I took the log of this side, I got rid of that negative, and I put that negative on that side. Don't forget your plus c's too. Okay, 2013, number 6. Do part A and part B. You see this differential equation when you read through. And a lot of people for part A just start solving it. Part A has nothing to do with solving the differential equation, nothing to do with separation of variables. Read carefully and see, I just want an equation of a tangent line, and I need to use it to approximate a function value. Okay? So do that for part A before you start separating your variables, which is what you need to do for part B. You get negative 0.6 as your approximation, I think. Yes. Well, do it again. Do it again, like you know what you're doing now, and see if you can get it. Okay, you get negative 0.6 for A. As you get through part B, make sure you're careful, separating your variables, finding the correct antiderivative. And if you're solving for C, and C is inside a log, don't be afraid. You can get rid of that log by taking e to the power of both sides. Now, a lot of people get y equals negative log, negative x cubed plus 3x squared plus c, and they plug in the initial condition, and they kind of freeze a little bit. And they stop at 0 equals negative log of 2 plus c. Well, there's a couple ways to do it. You could either know the value of log that equals 0, or you can just solve, right? You can take the opposite of both sides again. Well, the opposite of 0 is still 0. So I get 0 equals log 2 plus c. How do I solve for c? It's inside the log. Get rid of the log. How do you get rid of the log? E to the power of both sides. E to the 0 is 1. Turns out the log of 1 is 0. So 1 needs to be what 2 plus c is equal to. C is equal to negative 1. Giving me my particular solution, y equals negative log negative x cubed plus 3x squared minus 1. Okay? Let's do the next one. The next one's a little bit different. It doesn't have x's and y's. It has b's and t's. Really, it just looks like it has b's. All right. It's read, the rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. At time t equals 0, when the bird is first weighed, its weight is 20 grams. If b of t is the weight of the bird in grams, at time t days after it's first weighed, then dB dt is 1/5, 100 minus b. Let y equals b of t be the solution to the differential equation above with the initial condition b of 0 is 20. Part A has nothing to do with solving the differential equation. Part A is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? Explain your reasoning. Discuss with your neighbors. Compare your answer with a neighbor. Do we all discuss? Do we all have a good reasoning? Yeah? What's your reasoning, Miss Lowy? That is perfect. dB dt when b is 40 is bigger than dB dt when b is 70. Since it's larger, the rate at which the bird is gaining weight is greater than the bird is gaining weight faster when it weighs 40 grams and 70. Part B, I'm going to do part B because everybody messes up on part B. Find the second derivative, d squared b over dt squared in terms of b. Use it to explain why the graph of b cannot resemble the following graph. Well, the key to this is you need to find the derivative with respect to t of both sides of that. Now, that means I'm finding the derivative with respect to t, and I'm going to distribute the 1/5 to be 20 minus 1/5 b. Everybody says that this derivative is just going to be negative 1/5. But they're wrong. Why is negative 1/5 not the second derivative? Excellent, Mr. Kobayashi. Because I'm taking the derivative with respect to t, I do not have the agreement of variables. I would have to have a dB over dt at the end. So that means my second derivative here is equal to negative 1/5. They want it in terms of b, so I don't want dB dt in my answer. Well, how do I get rid of it? So I just have b's. I know what it's equal to. It's 1/5 100 minus b. So I actually have the second derivative as this. And I can distribute things if I want to. But they say, find it, found it. So I don't have to simplify once I find it. Use the second derivative to explain why the graph of b right here cannot resemble this. So this is the wrong graph for b. Why is this wrong? Well, the second derivative is going to be negative for all values of b between 28 and 100. So d squared b over dt squared is less than 0 for b between 100 and 20. What does that mean? And my second derivative is negative. B must be concave down throughout. It is not here, which is why that's wrong. Okay, now we get to part C. Now we distributed to take the derivative, but actually we cannot separate our variables if this is distributed. If I had my dB dt as this, we would not be able to do this correctly. I would not be able to get the b's with my dB correctly without some mess up somewhere. Okay? So you would leave it as a product. When do we go? 41? Okay. I would leave the 1/5 on the right side. It's not bothering anything. Just leave it there. But divide by 100 minus b, giving me 1 over 100 minus b dB, and then multiply both sides by dt, giving me 1/5 dt. And we're ready to antiderive both sides. What is the antiderivative of 100 minus, or 1 over 100 minus b? Nope. Recall, if I have something like this, x is to the first power, right? We would use the natural log function for the antiderivative. This would actually be natural log absolute 3x plus 4, but that's not correct. What do I need in front of it? I need the reciprocal of the coefficient of the x. This is actually negative log absolute 100 minus b. Okay? And the rest will be solving for b, which I'll do right now. Take the opposite of both sides before I get rid of the log. Take e to the power of both sides. Rewrite it so it's nice. I'll just go ahead and do the plus or minus now. Subtract 100, multiply both sides by -1. Still gets baked into the plus or minus c.
Do you need plus or minus to put the C?
I won't need the plus or minus when I find the particular solution. This is the general solution, the correct general solution. But now, b of 0 is 20. Don't need the plus or minus.
So if we were to just ask for the general solution, you still need plus or minus? Like that.
Yes. Typically, you won't be asked for the general solution ever. I've never seen one once when that's occurred. So if you want to skip the whole plus or minus thing, you actually won't be counted off if you don't include it. Now, before you go, it's important to understand that these free response problems, this is the one type of free response problem where most of the weighting is all in one part. If you looked at number 1 that we just did, it only got 2 parts, right? Well, unless I deleted a third part, which I didn't. Every single free response problem is worth 9 points. Typically, A is worth, in a situation like this, like 2 or 3. That means B is worth 6 of the 9 points. In most free response problems, it's like each part is worth 3 points each. You got, 3 parts, or a couple parts are 2 points, a couple parts are 3 points. This is worth a whole lot. But there is partial credit while you go through it. Separating your variables usually is worth 1 or 2 points. Finding the correct antiderivatives is usually worth a point. Using a plus C is usually worth a point. Finding the correct C is worth a point, and solving for Y correctly is worth a point. Okay? It's a lot of partial credit. It's really the one question where partial credit is given. It's an easy way to get a +9 on a free response problem. Okay? If you are portaled out, you may leave. Thank you very much.